just going to say a few words. All right, so this is the start of session 2 on productivity. Our first talk is called Spatial, a language and compiler for application accelerators, and Matthew Feldman will be presenting.
Okay. I'll just give it about 10 seconds and let everyone get a chance to get seated. Okay, so first of all, thank you for hosting the conference and having me here. I'm super excited to be here and meet other spatial developers. So my name is Matt Feldman. I'm a fourth-year PhD student at Stanford. I came into the Spatial project. So Spatial, I'll introduce it in a second, but has anyone actually used Spatial before or cloned our repository? Just want to raise your hand. Cool, okay, so 1 or 2 people have used it before. So I'm just going to introduce what it is, what some of the internals of Spatial are, and how it connects to Chisel. So, let's see. Okay, so the Spatial team has had a lot of people come in and out of the project. If you've seen or heard of Spatial before, David is the one who used to give the presentations. He has since graduated, so I've inherited the project. So it's a high-level DSL for programming accelerators. In the first session here, we talked a lot about some projects, some Chisel modules and designs that people have made. Hopefully Spatial is something that gives you a higher level of abstraction if you want to design accelerators. So the project has started around 2015. It's gone through a few different iterations at this point. It's embedded in Scala, just like Chisel, so we're familiar with Scala as we work on this language. It's the hardware reincarnation of what our research group has done traditionally, which is Delight, which was a framework for software compilers and parallelizing expansively across different architectures. And the paradigm with Spatial is that we came in with the idea that parallel patterns are the way to go if you want to design good hardware and good accelerators. So we have a few different things that we could target. So if you were to go and clone Spatial right now, you can run through our compiler and you could target simulation, VCS, Scala simulation. We have some Xilinx boards that currently work and we have some that we're working on, as well as some Altera boards. And ideally you use this language and we want it to be agnostic to which backend you're actually compiling to. So we use it in both education and it's used a little bit in some research and some industry. So we teach 2 classes at Stanford using this language. And we also have a few research groups at Stanford using Spatial for their projects. I'll talk a little more about that later. And there's a few companies, and Slack, the research lab near Stanford, are also using Spatial at some level in their stack. So just quick note about the talks that we had before. Some people came up here and talked about some of the projects they're working on, like FFT, matrix multiplies, convolutions, stuff like that. So I'm not going to stand here and argue that Spatial is going to give you something that is identical as these designs. And I'm really excited to go back and see if I could clone some of these projects and compare Spatial to some of these hand-optimized designs. What Spatial does let you do is quickly express an application at a high level and quickly explore different design choices and parameters within the application. So here's a brief overview of the flow of our compiler. So at the very back, you have Chisel, also C++ and Scala, depending on which backend you're actually targeting. We're going to talk about what's inside the Spatial compiler, so I'm just going to go over a few specific passes that I think are interesting within the Spatial compiler. And we're also going to talk about the front end, which is Scala, and some of the things that you can do as someone who only sees the front end of Spatial, what it lets you do in terms of designing good applications. So we're going to start with the back end. Originally, Spatial used a language called MaxJ, which I don't know if everyone is familiar with it, but it's a really good language if you want to do streaming applications. So the idea is you have data flowing into some hardware, and you want to compute and process it and send a stream back out. So as soon as you start adding back edges into your data flow, this language made it really difficult. So this is the main reason why we switched to Chisel. So some of the things that Chisel gave us were visibility into clock, whereas MaxJ, we only had some arbitrary view of streams, or ticks, which we found kind of tricky to debug. As I mentioned before, in MaxJ, once you start adding back edges, the compiler tries to do some smart things without having full knowledge of what you're trying to do in the application, and it makes it really difficult to actually make big, heavy designs. And we wanted portability, so Chisel, you could get the Verilog out the back end, and then you could wrap the Verilog into other Verilog and just target whatever board you want, so we could go to our Altera boards or our Xilinx boards. So now you could think of Spatial as having a library of Chisel templates. These Chisel templates could be controllers, state machines, counters, memories, all sorts of structures like this. And Spatial lets you design an application, and as you go through the compiler, it describes how to stitch together these primitives. So moving from MaxJ to Chisel, it solved a lot of our problems, and I'll just very briefly point out a few things that we found challenging early on. So for big designs, one of the things that we always run into is blowing up the JVM and the bytecode limit in Java, which we now have solutions to this, but early on it was just a minor setback. It took some time to rethink how we're going to emit out of the back end of our compiler. Verilator turned out to be a slow simulator for very, very large designs. So we've since moved to either Scala simulation, so we simulate the application in Scala, or we use VCS. And you still do have Verilator. If you do have a small design, you could actually use that. And we sometimes got random fertile errors back early on. We've since kind of figured out how to dodge these errors. We haven't solved them yet, but we don't run into too many anymore. So real briefly, I'm just going to give you a mental image of what a spatial application looks like. Let's say, so you write a program, and what you do in the program is you outline two pieces. You have a software piece. This is the part that gets deployed to the host CPU, and you have the accelerator. The accelerator consists of some pure Chisel Verilog, some algorithm that you're going to lay down in hardware, and we also give you a parameterized Chisel template that wraps around this. This is the thing that we call fringe, and this is the thing that lets you take some target-agnostic spatial code and interface it with whatever board or simulator you want. And we could also go directly to Scala, so if you want a quick simulation with no licenses or no setup, as long as you have Scala installed, you could compile, get Scala, and test your algorithm for correctness. So here's just a quick mental picture of how all these pieces fit together. I'm just showing DRAM here as an external interface that you might want to interact with. So you have a host, and you have the FPGA fabric. The Excel RTL, the thing that you write in Spatial, is going to get deployed into the fabric, as well as you have your executable in C++ getting deployed to the host. The fringe is the thing that lets you interface with the peripherals. So the fringe is the thing that lets you talk to DRAM, talk to register interfaces between the host and the FPGA, and also whatever streams you might have. So things like switches, LEDs, whatever board you're using might have its own interfaces. So that's about it for the backend. We could talk all day about how we use Chisel and all the things that we do in the backend. I'm going to just give you a brief tour of Spatial. So the next thing we're going to do is talk about the inside of the compiler. So here's just some of the passes that we do inside the compiler. It's not really important to read what these are. The idea here is we take something from the front end, which is the language that's embedded in Scala. It goes through a bunch of transformations and traversals, and out of the back, we get Chisel. So a few of these are more interesting than some of the others. So I'm going to just talk about a few of them very briefly. The first one I'm going to talk about is design space exploration. So as you're aware, if you're trying to write some application and you want to synthesize it and spend all the time baking it into hardware, you have huge trade-off spaces with parallelizations and tile sizes, scheduling of your controllers and how these pieces all fit together. So you don't really want synthesis in the loop. What Spatial gives you is quick design space exploration. So we have models built in the language, depending on what target you're going to run on. We have some empirical models. Some models we use information that we've trained on. So we have neural networks built into the language that, given some nodes in the spatial IR, we could get a sense of how much area it's going to use, and we could analytically compute the runtime and number of cycles that the application is going to take. as long as you don't have random accesses, in which case we just have to estimate. And we have, right now there's 3 different search mechanisms you could use in DSC. So we could do an exhaustive search, which is not really practical. Like a small design could have billions, trillions of points. So exhaustive quickly becomes unusable. We do heuristic searches, so we prune the space and we get a sense that we could kind of traverse the design space and look for good design points. And we also have something called Hypermapper, which is a separate project that is being worked on in our group. Hypermapper is just a more intelligent search through any arbitrary space. Hypermapper lets you do derivative-free optimization. It lets you deal with parameters that are real or categorical or ordinal. So we use all of these features. If you're designing hardware, for example, controller scheduling is something that is not a real or ordered variable that you have to work with. So moving on to the next pass in the compiler, we do memory analysis. So generally, this is the pass that takes the most time in our compiler. What memory analysis means is we deal with the banking and the buffering of all your memories. So given some access pattern, given some arbitrary nesting of controllers in your program, we're going to analyze the access pattern, and we are going to figure out how to bank it safely such that when you're running the application, you never have bank collisions, and we're going to try to use the minimum area possible. So we base our banking analysis on previous work, but we've extended it a little bit for our purposes. So originally, you could do an exhaustive search. You could look for different banking schemes, look at your access patterns, and just figure out which banking scheme provides no collisions. So we do a little tweaks to the search pattern when we're looking for banking. We have some cost models built in. For example, there's some cases where you want to duplicate a memory rather than bank it. So the compiler needs to be aware of this, and it needs to be able to make the trade-off and figure out what the best scheme is. We do have limited access for modulo access patterns. So banking analysis the vanilla banking analysis is just going to look for affine patterns, but not everything looks like an affine pattern, so we have some tweaks that let you do more complicated access patterns and figure out how to bank these. And we also look at the broadcastability of accesses. For example, if you have a read to a memory, which happens in multiple places in your application, the compiler is able to look down the controller stack and figure out if these accesses will happen in lockstep, in which case it could combine the memories and broadcast the access to different readers. So there's a lot more in memory analysis, but real briefly, that's kind of the general sense of what we're doing there. So the next thing is unrolling. It's a pretty straightforward transformation, but it's the thing that lets you have really tiny source code and explode it into really complicated and heavy applications with good performance. So here's just a really brief sketch of what unrolling kind of looks like. You start with something on the left that is relatively simple. It kind of maps to what you wrote in spatial code. And the unroller is the thing that will take the graph and just expand it and explode it and copy and vectorize whatever it needs to give you a good application. So the thing is, when you start on the left, you can't really map these to the Chisel primitives. After unrolling, that's the first time where you can actually take the spatial IR directly and map it to the Chisel templates that we're going to stitch together. There's a few things missing here. For example, I point out that it's not retimed. So retiming is another pass in the compiler that will look at the primitives within each of these controllers and figure out how to retime it so that you could hit high clock rates. So unrolling is essentially cloning subtrees in the graph, keeping track of the memory analysis that you computed before, and vectorizing the innermost controllers. So the last thing I want to talk about is retiming, which is also not a super creative pass, but it's something important and it's something necessary if you want to have good designs. So if you want to hit a high clock rate, you need to retime all your primitives. You need to put some retime registers in there so the synthesis tool can basically lay out the computation in a smarter way. So we do this for you. There's a lot of graph traversal stuff going on in the compiler. It's not too important to understand how it works or why. But one thing that I want to point out is that the compiler does have specific cases where it will optimize things for you. So a lot of times in your applications, you have reductions. These reductions could be additions. You could be summing a bunch of numbers, or you could have fuse, multiply, adds all throughout your reduction tree. So what this means, if you have a reduction, you have a register, and you want to accumulate something into that register, the back edge that goes from the output of the register back to the input of the register, you have to account for the retiming of the operations in that loop. So a lot of the common cases, we have special accumulators where if something, for example, has a 10 cycle latency, we will clone that register into 10 lanes so that you can issue a new value per cycle, and this is what gives you high performance controllers. So that's about it for the spatial compiler. The last thing I want to talk about is the front end and what it looks like as a user interfacing with spatial. So we're embedded in Scala, just like Chisel, and we make heavy use of Scala macros. So previously, the Google presentation mentioned they avoided those. We came in and we fully embraced them and we use them all over the place, which is good and bad. But it's what lets us give you a language and a front end that looks familiar and doesn't look too crazy. And the main idea with spatial is we want to raise the abstraction of programming accelerators, but we also want to have a hardware mentality when you go in to write an application. So for example, one of the things that we give you as a user is instrumentation. So if you're trying to write an application, let's say matrix multiply, and you want to figure out how to balance your pipelines and how to structure your controllers so that you get something that runs quickly, we give you instrumentation information directly in the back end of the compiler. So you compile your application, and you get something that looks like this. So it's not important to read what's in this screenshot. This is just an example of what the tool gives you. And the idea here is the blue links in each of these boxes will link you back to your source code, and they will link you back to a controller or a loop in your source code. The red text is telling you cycle runtimes. So whether you're running on the FPGA or simulation, you can turn on instrumentation counters in all of these loops and figure out where all your cycles are going. There's also in the black text some information about the scheduling of your controllers. So this tells you how, given some parent controller, how are the children interacting with each other and which one is the bottleneck. And finally, the last thing at the bottom right, there's some colorful boxes, and these boxes are useful for figuring out where all your memory usage is going. So in a lot of cases, when you have an application that looks relatively small, it could unroll into a lot of small stages, and we do the banking and buffering for you. So this means you could have a lot of buffering, and you could have deep buffers in your application. This instrumentation will help you figure out where those deep buffers are and help you figure out how to use less area in your application. And the final thing is, I think some of the previous presentations touched on this, but I'm just going to say it up front that metaprogramming it's confusing, but it's a really good way to write really good code. So you don't have to use metaprogramming to use spatial, but we do have information, and we have some tutorials on how to use metaprogramming, which is mostly just a tutorial on using Scala to your advantage. So metaprogramming is the way where you let Scala compiler do the heavy lifting before you actually enter the spatial application. So it's just kind of another layer in front of spatial that uses pure Scala. So if you're a Scala expert, you could use this to your advantage. The other thing about metaprogramming is we never intended for spatial originally to be its own language. We intended it to be an intermediate representation for other frameworks. So two of the ones that I mentioned here are TensorFlow and Halide. So we were originally trying to give ourselves some debuggable landing pad for this. And turns out metaprogramming is really useful if you want to build more layers on top of spatial. And also we use quasi-quotes to work with type. So the drawback, as I mentioned before, is it's challenging to use. You need a lot of type evidence. And as one of the students in our group pointed out, he compares using evidence like this to investigations. So, so just to recap, spatial is a high-level DSL intended to capture information about programming hardware and raise the level of abstraction to people who don't necessarily know Verilog or hardware design. But if you do know these concepts, you will design better code. We give you tools for performance and debugging your performance. We do a bunch of transformations for you, so you only have to tweak a little bit of source code to get big changes in the output. and it's built around stitching Chisel templates together, and we use it in a bunch of places currently. So that's all I have. Thank you for your time.
If there are any questions, please come up and use the mic, but I guess I'll start with a question. When you see errors, where do you see the errors usually? Is it in the type checker? Does it happen in Spatial? Does it propagate down into Chisel and Fertile and cause sort of confusion? Or like, what does it look like when you make a mistake using Spatial?
So the question is, when you make a mistake, where do you see the mistake? In the early days, a lot of the mistakes propagated all the way down to Chisel. So we've since figured out how to make this safe and how to not get errors in the Chisel compiler. Most of the mistakes that new students make and new people using Spatial make are generally pipelining mistakes. So they don't consider loop carry dependencies, and they don't consider initiation intervals, so they parallelize something that isn't technically safe to parallelize, so you don't actually get any speed up. And then if you actually do make a syntax error or a type error, at some point early on, you'll see this either in the Scala compiler or early on in the Spatial compiler. There's pretty much a sanity check after most traversals and transformations of the IR.
What's your plan for dealing with the changes to macros in Scala 3?
So that's a good question. The simple answer is we don't have a solid plan right now. We're going to work through it as it comes.
To me, it sounds kind of like you're doing something similar to high-level synthesis. Can you like sort of compare with previous approaches there?
Right, yeah, so the question is, it looks like HLS, and that's true. We came into this hardware DSL world with the idea that if you want to write good hardware, you want to start with parallel patterns, and you want to start with a language that looks native and natural to a hardware developer. So HLS is, you're basically writing C, and it's kind of hard to figure out exactly what's going on. So you write code that you know works in software. As far as what's going on with the hardware behind the scenes, it's a little tricky, and also it becomes a little awkward when you start to add pragmas all over the place. So Spatial tries to capture all this more natively. And then the other thing that we came in with is also, if you want to have good code, you need pipelining at different levels in your hierarchy. So if you have a bunch of nested loops, you want to be able to pipeline all of these loops and understand how this pipelining works. So this is something we call coarse-grained pipelining in our language. At least when we started, HLS only let you pipeline basically at 2 layers, at your inner layer and some outer layer.
Thanks.
All right, let's thank the speaker.